Every day, up to 70 trains pass over this section of track. Each time, the engine and the coaches exert a downward force on the rails, the chairs and the sleepers. There's a force acting on this coupling. It's the force that's needed to accelerate all the coal wagons behind it. Every time an aircraft lands, its landing gear is subjected to very large forces. An aircraft like this might land up to 1,000 times each year. The safety of each landing depends largely on the ability of the landing gear to withstand the large forces involved. And here, among the trees, forces are acting on the suspension and other component parts of this vehicle. Sure, this type of vehicle will stand up to years of heavy service. It's tested in a special rig. Here, it's being repeatedly subjected to the kind of forces it will meet in service. It's a fatigue test. In service, materials constantly encounter forces, and they must be chosen and designed so as to withstand them. But they also encounter forces in manufacture. Here, we're using a force to forge a steel billet into the shape of a roller. And the roller can be used to exert a force on red-hot slabs of steel in a rolling mill. This is how sheet steel is made. And in the press shop, the sheet steel encounters a force when it's pressed into the shape of a component. In this case, we're pressing out parts for cars. Both in service and manufacture, materials are constantly subjected to all kinds of forces. So it's important to understand how a material behaves when a force is applied to it. Here we're applying a downward force to a block of material. You can't see the force, so we'll represent it by an arrow. Although the arrow's in the middle, the force is distributed equally over the top surface of the block. Now, when a force is applied to a material, the material resists with an equal and opposite force. If the downward force is increased, there's an equal increase in the resistance. A material in this situation, in the act of resisting a force, is said to be in stress. But stress doesn't only depend on force. Here are 3 blocks of the same material. Each has a different cross-sectional area. The one on the left has an area 4 times the one in the middle. And the one on the right 16 times the one in the middle. Right, now we'll apply the same force to each block. The same force, the same resistance. But what about the stress? Remember, in each case the blocks have different areas. For the one in the middle, the force is applied over this area. For the one on the left, the same force is applied over 4 times the area. That's equivalent to 4 small blocks, each encountering only 1/4 of the force. For the largest block, the force is applied over 16 times the area. That's equivalent to 16 small blocks, each encountering a 1/16 of the force. In each case, the stress is different. The one under the greatest stress is the one with the smallest area. So, stress depends on 2 things, force and area. It's measured as force per unit area. Now, there's something else that happens to a material when a force is applied to it. Here, we're applying a very large force to a block of material in a compressive testing machine. Can you see what's happening? It's becoming deformed. Its dimensions are changing. In particular, its height has changed. If we compare this with the same block before it was deformed, we find it's lost height by this much. If we divide the loss of height by the original height, we get a new ratio. This ratio, change in height to original height, is known as strain. Let's take a closer look at the practical effect of applying a force to a material. In this machine, we're going to apply a pulling force to a piece of steel. By attaching a suitable meter, we can see how the steel behaves under the action of the force. With the meter set, we can now apply the pulling force. Immediately, the steel begins to stretch. The greater the force, the more it stretches. We'll stop at this point and see what happens if we remove the force. The steel has returned to its original length. This kind of behavior is described as elastic deformation. Here's a typical example of elastic behavior. The springs. When a force is applied to them, they deform. When the force is removed, they go back to their original shape. But elastic behavior doesn't only occur in springs. Can you see anything wrong in the way this lathe tool is being mounted? Well, let's take a cut and see what happens. The noise you hear tells us the cutting tool is vibrating. It's behaving elastically. That's because it's been mounted with too much overhang. Let's see what effect this has had on the work. A poor finish. Cutting is one instance where elastic behavior must be avoided. Now let's go back to our piece of steel again. We know that up to a certain force, this material will behave elastically. What happens if we apply even more force? The steel continues to stretch. We'll stop at about 25 units and see if the steel will still go back to its original length. It isn't going to. It's become permanently deformed. Now, permanent deformation has a useful application in engineering. Here, it's an essential part of a common process in a car factory. Imagine what would happen if the sheet steel behaved completely elastically. A similar machine and another process where permanent deformation is required. This is the process of forging compressor blades for aircraft engines. The material is titanium. In a single blow, a complex shape is formed. Each engine requires a considerable number of these blades. Imagine the problems of machining this type of component out of a bar. But permanent deformation can occur as a result of bad practice. This chap is using a homemade clamp to restrain a job for drilling. Is he using it the right way? Can you see what's happening as he tightens up the nut? The clamp isn't restraining the work properly. Nor is it resting firmly on the packing piece. Perhaps if he slackens off the nut, the clamp will straighten itself out and hold both the work and the packing correctly. But no, the damage is done. It still isn't restraining the work properly, and the same goes for the packing. It's permanently deformed and no more use as a clamp. Here's our piece of steel again. Now, so far we've seen that up to a certain force it will behave elastically. Exceed that force and it becomes permanently deformed. What happens if we apply an even greater force? Eventually, of course, it fails. This is the kind of behavior we usually want to avoid in engineering. But even failure has its uses. In all cutting operations, something has to fail, and that's the work. Cutting a material involves causing it to fail where we want and how we want. Cutting tools bring about failure by applying a very large force to a very small area. But in cutting a material, failure can occur where you don't want it, as a result of bad practice. Here we're using a tungsten carbide cutting tool. We'll stop the work rotating without disengaging the feed. With the feed still engaged, we'll start it up again. What's happened? We seem to have damaged the cutting tool. Restarting with the feed still engaged applied an excessive force to the cutting edge and part of it has broken away. It failed. Forces can be applied to materials of which components are made in several different ways. Take this hydraulic hoist, for example. The piston rod is being pushed down at one end by the weight of the engine. At the other end, it's being pushed up by hydraulic forces on the piston. In other words, it's being compressed. These forces are known as compressive forces. While the piston rod is being compressed, another part of the hoist is being pulled. That's this part here. These forces are known as tensile forces. We often find these forces acting on components. But what about the forces acting on the jib of the hoist? At one end, the load is pulling down. Further along, the piston rod is pushing up. We call this action bending. Bending forces can be encountered when cutting materials. Here, the ram is pushing the top of the tool forwards. At the cutting edge, the work is pushing the other way. A force acting at one place is counteracted by an opposite force somewhere else. Here's another case of two opposite forces. A prop shaft is turned in one direction by the engine. At the other end, the road wheels resist being turned. This has the effect of trying to stop the rotation. We can see what effect that has on a material in this experiment. By turning this wheel, we can apply a rotational force to one end of a steel shaft. This pointer is attached to the shaft. Further along, there's another pointer also attached to the shaft. And at the far end, the shaft is clamped so that it can't rotate. Let's see what happens when we apply a rotational force at the other end. Can you see what's happening? The shaft is twisting under the action of the force. The rotational force at one end of the shaft is opposed by a similar force at the other end. The name given to this action is twisting. It's very common in axles and shafts. It's also common in drills. The twisting force here has the effect of trying to straighten out the helix of the drill. This cropping machine shows another way in which forces can act. It's another case of two opposite forces, but here the material fails. The upper blade exerts a downward force. This force is so close to the upward force exerted by the lower blade that there's no room for the material to bend between them. So the material fails. We call this action shearing. There are many examples of shearing forces in the workshop. Tin snips, and of course the guillotine. A punch also depends on shearing action. When the punch pushes downwards through the hole, it pushes a section of the material with it. In service, materials encounter a variety of different forces, and in many cases, more forces are at work than are obvious at first sight. It's worth studying components in action and working out exactly what's going on. In this case, it's easy to see that the rails, the chairs, and the sleepers are all being compressed by the weight of the train. But what about the fish plates? What sort of forces do they meet with? What about the bolts through the fish plates? And what about the unsupported ends of the rails? We'll leave that for you to think about.